So, welcome to online video lecture for the subject high voltage DC transmission. So, on the topic I would like to discuss now is a design of filters in HVDC transmission. Okay, so coming to the design criteria of these filters. Okay, so why we go for filters? First of all, later on we can think about what are the criteria. I mean, what are the requirements and what we need to take the what we are going to take the considerations. Okay, so in order to design the filters. Okay, first of all we must recall what are the functioning of these filters. Okay, so why we need to place in the especially in the HVDC transmission. So of course we might be knowing in the coming to the power systems. So because of the any issues, any power quality issues, if we consider, so either voltage variations, voltage spikes, or voltage sags, well, or harmonic distortions, interharmonics, supraharmonics, likewise. Okay, so different issues may arise. So whatever may be the cause, short circuits or any dynamic load changes, or because of any three-phase faults, or because of any internal faults, or any abnormal conditions, unsymmetrical valve conduction, or any characteristics variations in the switches, or because of any saturations, or because of any bias. Likewise, many issues arises, and of course we are discussing particularly on HVDC. Okay, so the purpose of placing the filters here is, so there exists the two cases, that is at the AC side and at the DC side. Okay, so we need to filter out the harmonics, that is in case of DC we are calling it as ripples. Okay, so coming to the AC side, so we are calling it as an harmonics. Of course there exist different types of orders there. So I think I have a, fundamental concept, that is the harmonics is itself is defined as the integral multiples of fundamental frequency. So the source of the harmonics is the AC there. So in case of HVDC, if we are going to discuss, so the source of the harmonics is the AC. Okay, so the input what we are feeding there, or of course coming at the inverter part. Sorry, one second. So coming to the inverter side, there we are going to convert the DC to AC. Okay, of course there also exists some harmonics. So we need to filter out these harmonics what are generated. Okay, irrespective of the order, we need to filter out at the two ends. Okay, so coming to the intermediate station, so that is the DC part. So there also we need filters. Okay, all right. So before that, so before placing these filters, so we'll see one by one what are the design criteria. An ideal in filter design is the elimination of all the detrimental effects caused by waveform distortion, and particularly telephone interference. Okay, so in case of the HVDC, so we are particularly focused on the telephone interference. Okay, so what do you mean by telephone interference, or TA in the sense? So because of these power lines, okay, so this it generates a signals which is going to interfere the communication lines. Earlier we have seen, so that is the either railway signals or the communication signals. So likewise, okay, so it is going to interfere. Okay, of course the power lines as well as the communication lines, if they are very nearer by each other, so this is going to interfere. So we need to calculate that. So what is the tolerance level, and whether it is exceeding or not. So for that, what we are going to what we are going to perform based on which standards, whether it is following the standard or not, any deviation in that we need to cross check it. So for that we need to find out this telephone interference. Okay, however, this ideal criterion is unrealistic because of the difficulty of estimating in advance the harmonic flow throughout the AC system. So simply as per the statement, once again. So as per the statement, we can say that just placing by filter, we can reduce the harmonics, but that is not the case. Okay, so before placing of the filter, so we need to analyze what is the order of the harmonics, and what is the frequency level, what is the magnitude there. So for that particular frequency, how can we eliminate those particular harmonic? Okay, so before placing a filter, we need to analyze what is the what is the actual representation of that harmonics. Okay, so here it is not realistic there. It is unrealistic in the sense it is not quite easy manner to just place a filter so that it will be biased. So that is not the case. Okay, next, it is also uneconomic, and in the case of the telephone interference, the problem can normally solved more economically by taking some of the preventive action in the telephone system itself. Okay, so of course, we are not completely relying on the power system. I mean methods. Okay, so not about completely relying on the placing the filters or any other composition techniques. It's not about that. So we have to concentrate at the telephone lines also. We need to regulate it. Okay, so in order to by taking certain actions like making a distance, okay, or providing any proper insulation there. So likewise some measures will has to be taken, so that is by default there. Okay, next, a more practical solution is the reduction of harmonic voltage to an acceptable level at the converter terminals. So as I said you before, so these power lines, it depends upon the high operating levels, high operating voltage levels. Okay, so these power lines, it is going to interfere the telephone signals. So means in the carrier, so that means through air or some other medium, so a millis of volts will be generated and it is going to interfere the communication lines. So that those millis of volts which is having certain amplitude and having certain time period, okay, we need to reduce that. Okay, so that we can reduce this interference. Okay, so acceptable level in the sense, how can we justify means based upon the equation there, later on we'll see. The flow of harmonic current causes no special problem provided that the system harmonic impedance is small, and therefore a criterion based on harmonic voltage rather than current is more convenient for filter design. So as I said, if you want to place a filter at the AC side, so it is not a big issue. Okay, so because the impedance, we are connecting the shunt impedance there. Okay, so this shunt impedance will not create a much issue in the line because we are adding the impedance. So adding the impedance means what it leads to, there may be chance of increase in the losses or increase in the line reactance. Obviously some issues will be there. So if we are attaching anything to the line means obviously there will be a change in the system parameters. Of course, by placing these filters, it will not be a much issue because all the impedances which we are choosing for this harmonic reduction, it is of very less. Okay, that is the case. Typically specified factors to be taken into account in filter design. So in that, let us see one by one what is the factor uh, to design a filter, okay, in order to reduce the harmonics. So in that, first thing is voltage distortion. So what do you mean by voltage distortion? The name itself indicates that there are certain distortions in the voltage waveforms, and how long we can accept for it. Okay, so whether it is a standard or not. So by this equation we can analyze. So voltage distortion caused by individual harmonics. Okay, so there are certain standards in the power quality there. So voltage distortions, voltage spikes, voltage sag, swell, voltage fluctuations. Okay, so likewise there are certain standards. So how many milliseconds in the the condition should be there, what should be the amplitude, whether it is 0.1 per unit or 0.9 per unit or exceeding 0.9. Okay, actually we require 1.0 per unit, which is the reference value. Okay, if it is above these limitations, so what happens, we need to think about it. It comes under one of the power quality issue. So in that, voltage distortion is one of the issue which is caused by these harmonics, individual harmonics. Okay, so individual in the sense, what does it mean? So third order, it's an individual component. So fifth order, it's an individual component. So 5, 7, 11, 13, 17, 19, 21, likewise. So order of the frequencies, it is of individual components. Okay, so as I said before that if the order is high, the severity will be less. Okay, so the effect on the system will be less. If the order is low, suppose for example 3, 5, 7, so it has a greater impact on the system because the magnitude of these harmonic components are high. Okay, so coming to the voltage distortion, we can measure with this equation. So V suffix TD, total distortion, equal to root of uh, summation sigma n equal to 2 to infinity. So we are starting from second harmonic to infinity. So there may we can suppose if we consider the power quality analyzer, it is a kit we use to measure the harmonic component also right now. So with that we can measure up to 40 to 50 harmonics. Okay, so I mean, and if the order is from 3 5 7 likewise and so on. So if I start from 3, so up to 40 harmonics it can measure what is the magnitude, what is the time period there. So with that harmonic, what is the change in the voltage and what is the total harmonic distortion, everything we can get. Okay, so these are the earlier theoretical calculations there. So right now everything we can get through the equipment there. Okay, so what is the value? Root of sigma n equal to 2 to infinity vn square. Okay, so where n gives the number of harmonics, order, I mean number of the harmonic component. Next, telephone influence factor. So it is also termed as TIF. So the TIF gives an approximation to the effect of distorted voltage or current waveform of a power line on telephone noise without considering the geometrical aspects of coupling. See, especially this can be observed during the night times of the, if we are nearer to the transmission, I mean, near in the sense if we are looking towards the high power transmission HT lines. So there we can hear some sort of noise. So that noise should not interfere in the telephone lines. Okay. So if there are any communication lines near to these type of high tension lines, okay, so these noise are going to interfere with the communication lines. Okay, and see, look at this. This TIF gives the approximation effect on the distorted voltage or current waveform. So that's what I mean. Power line in the sense, if we suppose consider the DC power line, so there exists only the two components, that is the voltage and frequency. If any of these waveform gets distorted, means obviously the power level, the power also gets distorted. Okay, so that distorted waveform is going to be fed to the inverter. Okay, or at the rectifier it has some impact. Okay, it creates some noises and all. So this TIF is completely not at all considering the geometrical aspects of coupling, means I mean they're not considered about the axis or a magnitude or a shape of the waveform and all. Okay, so what is the TIF? We'll see. The harmonic frequencies that are sensitive to the ear are given with high weighting factors. Since even if the harmonic magnitudes are small, these harmonics may result in unacceptable telephone noise. See, earlier there are certain equipments that are there, that is a sophometric weights. So which is the term is used for or this you can see here from this equation C PF, P suffix F is the C message weighting. So these are the one of the measuring components. We can measure the magnitude of the noise. Okay, so what is the, I mean what is the magnitude there? Okay, I mean in terms of decibels. So whether it is audible or not, I mean whether it is whether it is accountable or not, so whether it is crossing the limits or not, everything we can measure with the help of these weighting factors. Okay, so that is nothing but a sophometric weight, we can term it as. Okay, so based on that we can find we can use this equation. So that is TIF equal to 1 by V. Okay, that is the fundamental voltage there, into sigma f equal to 0 to infinity kf pf vf whole square whole to the power 1 by 2. Okay, so where kf is the constant there, so it depends upon the 5 times of the harmonic frequency there. Because see, coming to the ripple content there, continuously, if we consider the DC ripples, let us consider the DC ripples, so it has certain frequency. Okay, so the frequency is continuously varying there. So if the frequency is continuously varying, what happens? So what is the source of that frequency? So again, the same, the fundamental component. So let us consider from the AC side. Okay, here we have taken the fundamental AC voltage. Okay, so for this frequency, what is the source means? The fundamental frequency. As per the definition, what we have discussed, that is the integral multiples of fundamental frequency. Okay, so this harmonic frequency completely depends upon the source frequency. Okay, so this is the equation, that is a telephone influence factor, which is used to measure what is the range there. So based on this, we are going to design the filter. If the noise levels are high, so what is the magnitude there, and what is the value of that influence factor, we can find it out, and based on this we can design the filters. Okay, I mean we can choose the components, so according to their interference. Okay, so where Vf is the harmonic sorry, RMS voltage of frequency F on the power line. Okay, next, this is the Vf in the sense if the harmonic component, if the harmonic voltage component we have considered, so that is the magnitude of that harmonic. Okay, so as I said you before, these harmonics also has certain magnitude and certain frequency it will travel. Okay, right, and this equation we can also use V equal to sigma f equal to 0 to infinity Vf square whole power 1 by 2. So based on this we can find out the voltage. Okay, so how much distortions are there, I mean how much of millivolts are generated to this fundamental voltage. Okay, so how much distortions are obtained we can calculate. Next, harmonic distortion. So this can be measured in two ways. So if consider D as the harmonic distortion or HD, so that's up to you, which is equal to sigma n equal to 2 to m. Okay, in Zn by E1 into 100. So where in Zn and E1 are the harmonic currents injected. So that is because of this because of this harmonic current, so there we are going to inject the impedance value as well as the particular voltage there. Okay, so this is the harmonic distortion equation. Based on this we can find out what is the total harmonic distortion. So another equation also can be used. So that is sigma n equal to 2 to m. So in Zn whole square whole power 1 by 2 by E1. So you can be having a small doubt that where these equations are derived, in the sense as per the earlier standards or earlier testing methods they have given this equation. So these are the design criteria. Based on this we are going to design the filters. Okay, so these are the already predefined equations there. Just we need to just consider that equation, no need to go in brief of how these equations are derived and all. Okay, so that will be out of our scope there. Okay, next, so that's all about the design criteria, and let's come into the design factors. So coming to the design factors, two basic concepts in filter design are filter size and quality. Okay, so filter size means that is the only metric there. That is, if you want to the filters are common for both AC and DC. Okay, so we need to filter out all the harmonics with the help of these filters, but the only difference is different size. Okay, and the quality, in the sense it's not about the component quality, but actually it means the quality. I hope you heard about the quality factor, right? So what is the function of the quality factor? So how much of energy is absorbed and how much of energy is released. Okay, so based on that what I can say, um, based on that given in facts we can term it as 1 second. Okay, so that's about the quality factor there. Next, the size of a filter is defined as the reactive power that the filter supplies at fundamental frequency, which is substantially equal to the fundamental reactive power supplied by the capacitors. See, also we know that it's not about the DC side, we are discussing about the AC side. So these filters which we are preferring for the harmonic reduction can also be used for reactive power compensation. Okay, so to certain extent, because we are using the different combinations of RLC components there. Okay, which are nothing but the energy storing elements. So the either inductor or capacitor, definitely one of the components will be chosen there. Of course R is not mandatory, but any of the energy storing elements we need to prefer, either it is an RLC series circuit or RLC parallel circuit, or combinations of different LNC components, either high pass filters or low pass filters or some other tuned filters, anything. Okay, so any of the filters they can act as a reactive power compensators based upon our switching techniques. Of course it depends on the switching techniques also. Okay, so that's what it means. So especially it comes under the AC side, but coming to the DC, There is no concept of frequency. Obviously, there is no concept of reactive power. Okay. Next, the total size of all the branches of a filter is determined by the reactive power requirements of the converter, and by how much this requirement can be more economically supplied by the AC generators, extra shunt capacitors, synchronous condensers, or static wire systems. See, if let us see from this figure. See, look at this figure. This is the HVDC converter station there. Okay, so at the AC side, either it may be before rectification or after inversion, so we have connected the filters. Okay, so all the, if we calculate all the filters which are shunt connected, and we will be having an idea that to which extent we can compensate the reactive power by using these filters. And for the remaining thing, we can we can utilize the what they have given, that is the generators, shunt capacitors, I mean statically mechanically switched capacitors or mechanically switched reactors, or else we can go for a synchronous condensers. Okay, so based upon the over excitation and under excitation, we can compensate the reactive power, as well as we can prefer the one of the FACS component, that is the static wire systems. Okay, so these filters, if we count with all the filters what we have attached to the AC side, of which is of parallel connected, so we can compensate to certain extent the reactive power. So the remaining thing we can depend on this any of the components. Okay, I hope why we prefer a reactive power compensation, we are familiar about this reactive power and all. Okay, we are not going in detail of the reactive power concepts. Okay, so only one thing we can highlight it at to maintain the system stability. Okay, if any of the system variations are appeared, if any voltage or frequency variations has happened, obviously the system leads to abnormal condition, and we need to make the voltage constant there. Of course, frequency cannot be immediately gets varied. It is a rare case. But coming to the voltage, there are more chances of voltage variations. Okay, so I mean voltage variations in the sense it cannot maintain the constant voltage under running conditions. So in order to make it as stable, so we are going to compensate the reactive power, and all these are interrelated. Okay. Next, the quality of a filter. So Q expresses the sharpness of tuning and is therefore defined differently for tuned and high pass filters. So before going for this tuning of filters, we must know why we go for tuning. Okay. So if we prefer any particular type of filter which has the RLC components, if we vary the frequency, so obviously the reactance is going to be varied. How we are going to perform this variable frequency means, if we consider the shunt component, let us consider the shunt filters, sorry, shunt connected fax components. So what are the fax components? That is, if you consider a STATCOM or SVC, SVG, or FCT, TCR or TSC, likewise any of the component if you prefer. So all these are shunt connected. So we are going to inject the current. So how this current can be controlled means, so this current is the flowing through the filters, not about the fundamental current. Okay, so this is the harmonic current. So this current I can control with the help of the switches. Okay, so based upon the switching operation performed, we can control, we can vary the frequency, which leads to variation in the reactance. Obviously, if the reactance is varied, the impedance is going to be varied. Okay, if you are varying the impedance means, so that is nothing but that operation I can call it as tuning. Okay, so it depends upon the harmonic component. Okay, so what is the frequency of that particular harmonic, whether it is a 25 hertz or 25 kilohertz or 100 kilohertz, that's up to the harmonic frequency. Okay, so whether it is third order or fifth order. Okay, so that's up to the harmonic component. Okay, so I think you have the idea about the, suppose if I consider the fifth harmonic. Okay, so that fifth harmonic will be having certain frequency. Okay, it may be 100 to 150 kilohertz. Okay, that is the speed of the, I mean that is the I mean angular velocity of that particular harmonic, and it will be having certain magnitude. So in that particular frequency we need to suppress with the help of this impedance. Okay, so that's the case. Okay, next, the sharpness of tuning of a resonant filter branch increases with the ratio of its resonance inductance or capacitance to its resistance. Whereas in the case of a high pass filters, the sharpness increases in inverse proportion to the ratio. So sharpness of tuning of resonant filter in the sense, once again, okay, sharpness of tuning of resonant filter. So resonant filter in the sense, so why I think we know about the resonance condition, which should not be happened in case of the power system there. Okay, so in order to avoid the resonance condition also, they prefer these type of filters, so which is a combination of different energy storing elements. They have given the case. So what is what is the condition there? The filter branch increases with the ratio of its resonance inductance. Okay, so that means if the inductance is high, we are going to compensate with capacitance, or if the capacitance reactance is high, we are going to compensate with the inductive reactance. So that is the balancing there. Okay, next, the high Q or tuned filter is sharply tuned to one or two of the lower harmonic frequencies, such as the fifth and seventh. Okay, as I said you before, lower harmonics are the dangerous harmonics, and we are particularly placing these filters. Okay, so we are neglecting about the third order, which can be eliminated by using the winding interchange, winding star to delta conversions there, winding conversions there. Okay, so especially if you think about the fifth and seventh harmonics, we need to particularly place the filters. Okay, so that depends upon the quality, high Q or tuned in the sense, based upon this harmonic component frequency and magnitude, we are going to design the filters. Especially we have taken the fifth and seventh. But what about the remaining other harmonics in the sense? It will be common. Okay, if the order gets increased, of course the severity will be less in the line, and we can place a common filters, so which can look after all these harmonics. Okay, next. The low Q or damped filter provides a low impedance over a broad band of frequencies and is often used to eliminate the higher order harmonics. That is an example up to 17th. Okay, so this is from the figure you can see here. So single tuned filter. Okay, so figure B is the single tuned filter impedance. Okay, so based upon the, see, look at here, at this if we consider this is the ratio of the resonance condition there, omega to the omega r. So there the impedance is resonance condition in the sense only the all the reactants are going to be cancelled there, so only resistance exists. So this is the minimum impedance offered. Okay, so minimum impedance offered means what happens, the maximum power can be delivered there. Okay, so this is the quiescent line, so that gives the quality of that, as I said before, quality factor of that particular filter. So which gives omega r to the, so total bandwidth there. Okay, so this is for the single tune filter. This is the filter circuit, and this is how the impedance offered for the harmonic component. Next, coming to the damped shunt filter circuit. So this is the series circuit there, and here it is the shunt circuit, and how the impedance is going to be varied here. Okay, so with the increase in the frequency, how the impedance is going to be changed at particular point, that is a quiescent point. So the minimum impedance will be offered there. So we need to look after the ratio there. Okay, so all these actions will be performed dynamically, and we need to no need to bother about how we are going to perform the switching action and all. It is dynamically performed there. Okay, because we need to focus only the fewer order harmonics, that is 3 5 7 likewise. So remaining thing, it is not a big issue. So only we need to concentrate on the these lower order harmonics. So that is why we are focused on this filter design. Okay, above figures shows typical circuit diagrams and the characteristics of two types, and figure A illustrates their incorporation within the conventional 6-pulse HVDC converter configuration. So this is the figure A, already we have discussed in the earlier sessions. So how these arrangements, so just we need to highlight that. So look at here, 5th, 7th, 11th, 13th harmonics and high pass filters. So high pass filters, as I said you before, if the order is very higher, if we consider from 17, 19, 21, 23 likewise and so on. Okay, so up to 40, around, take it as 40 to 50 harmonics. Okay, so for all those harmonics, commonly we can prefer these type of filters. Okay, for each and individual harmonics, we no need to design the filters. Only for especially these particular harmonics only, we are placing some individual filters. Okay, next. The diagram in the figure B indicates that the harmonic current generated by the converter divides between the shunt filters and the AC network. So you look at the figure B here. So this is the harmonic source. So what is the source of the harmonic? It is nothing but AC. So you look at here, it is a converter transformer. Okay, this is the simplified circuit for the harmonic source filter and the AC network impedance. So source of the harmonics means AC. Without AC, there is no harmonics at all at the HVDC station there. Okay, and it is the converter transformer. So these two are shunt connected. So AC for the AC network, we are connecting the filters or parallel connected there. Okay, so through this filter, we are going to eliminate the harmonic currents or harmonic voltage. That's up to the operation there. Okay, so this is a simplified circuit. Okay, nice. To be efficient, the filter needs to be of much lower impedance than the AC network, and ideally must not resonate with the AC network impedance. So that is the case here. Whatever the filter impedances which we are injecting in the line, of course shunt connected, it should not disturb the total line reactance. Okay, so if we consider the real power transfer equation as per the fact subject which you have seen, so P equal to VSVR by X into sin delta. If total reactance is made zero, what happens? The real power transfer is infinity, which is not practically possible there. Okay. So, but from that equation, we can come to a statement that if completely reactance is made zero, there will be high amount of power will be delivered for a short period of time. Okay. So that should not be happened. By placing the filters, a resonance condition should not be created in the line. Okay, so obviously they need to take certain measures. So as I said before, if the reactance is high, if because of the inductive reactance, if the total reactance is high, we need to compensate with the capacitive reactance. If the capacitive reactance is high, we need to compensate with the inductive reactance. So that is what we are performing with the help of the fax devices. Okay, right. So finally, therefore, the key to good filter design is a clear understanding of the two components of the equivalent circuit. So from this, we can conclude that for a good filter design, so there are two components. What are those? One is the harmonic source. Okay, because if the source is very clear, if the source is very perfect, and if there are no distortions or if the voltage and frequency are fine, if there is a pure sinusoidal waveform, most of the harmonic content can be reduced. Okay, and what about the other case? The impedance of the AC network at harmonic frequencies. Okay, so this impedance, okay, the total line impedance should not be affected with the help of with the filter impedance. So we need to choose the proper impedance based upon all these factors. What are those? TIF, harmonic distortions, I mean um, harmonic form factors. So likewise. Okay, so those are the issues. So hope you have understood the session. So thank you. That's all about harmonics. Design of filters in a HVDC transmission. Thank you.